All right, let's get started. This is the second in a two-part series. If you are new to Arc Flash, then the first one I think would have been by far the more interesting. However, if you attended our first class or have some experience with Arc Flash, I think you may find this more interesting. We're going to get into some more advanced topics. I do have a few review slides at the beginning. These are the applicable standards, and most of the things we're going to talk about today come from NFPA 70E and IEEE 1584. As you know, NFPA 70E has the same number there as NFPA 70, the National Electrical Code. That's intentional. NFPA 70E comes out 1 year after the National Electrical Code. So the most current version of the National Electrical Code is 2020, but the one before that was 2017, and therefore the most current version of NFPA 70E is 2018. Now, this basically says that if you are within the limited approach boundary, which for most low voltage systems is 3.5 feet, and it's over 50 volts, that you are required to lock out the gear. There are two exceptions to being able to lock out the gear. One is if you have additional hazards or increased risk. For instance, if de-energizing would cause more danger than working hot, then you are allowed to work hot. And the second one is the most common, infeasibility. You can't do a drive startup, you can't do certain troubleshooting if it's not energized. And so under those conditions, you are allowed to work energized. And most of what we're talking about today has to do with working energized. You are required to be retrained every 3 years. And so that is retraining on NFPA standard, which is what we're talking about today. These are the boundaries. You have one burn boundary and two shock boundaries. The burn boundary is determined by where you are at risk of a second-degree burn. That is 1.2 calories per square centimeter. So when you cross that arc flash boundary, if there were an arc flash, then you are at risk of second and or third-degree burns. The limited space and the restricted space, which for most low voltage systems, the limited is 3.5 feet and the restricted space is 1 foot. They are based upon shock. And if you cross the limited space, you must be qualified or with a qualified person. If you cross the restricted space, you must be qualified and have the appropriate PPE. Now, labels. This is out of now IEEE 1584. The labels must be on switchgear, switchboards, panel boards, industrial control panels, meter socket enclosures, adjustable speed drives, machine control panels, and machine control centers. So those are not optional. All of those things you must have labels on. Other things you may have labels on depending upon whether you feel that you are going to have to work inside that box or that piece of equipment when it's energized. So things like busways, bus plugs, fused and non-fused disconnect switches, motor terminal boxes, transformers, not typically labeled, but if you want to label them, you're certainly welcome to. Now, the exceptions to labels are if there's been some kind of a change to the system that made the original label inaccurate, then you must change it. And secondly, in supervised industrial installations where conditions of maintenance and engineering supervision ensure that only qualified persons monitor and service the system, then you can have that information in a different place. It doesn't necessarily need to be in a label on the equipment. Here's PPE. We always look at the estimate of likelihood of occurrence. So they always like to make this somewhat difficult. Likelihood of occurrence means if it's likely that there could be an arc flash, you have to wear your PPE. If it's unlikely that there would be an arc flash, you don't have to wear your PPE. So as you can see, if you're going to read a panel meter or operate a circuit breaker, the likelihood of occurrence is no, and therefore you don't need to wear your PPE. If you're going to open things and expose yourself to live circuits, then you do need to wear PPE. And two that may not be obvious is if you're just inspecting for thermography or to take pictures in an arc flash study, or if you're only going to work on circuits 120 volts and less, actually says 125, then you do not need to wear PPE in those instances. But basically, anytime there's energized parts there and you are at risk for an arc flash, then you will need to wear PPE. What is the appropriate PPE? There's two ways of doing it. And I'm just going to, we covered both of them last week. We're only going to cover the newer one this week. That's the incident energy analysis method. And the incident energy analysis method is based on calculating the calories at that point. So if the calories are under 1.2 calories per square centimeter, which is the level that will give you a second-degree burn, then you just need to wear non-melting long-sleeve shirt and pants and your normal protective equipment. If it is from 1.2 to 12 calories, you will need to wear shirt and pants or coveralls rated for whatever calories of equipment you are working on, and then your typical safety equipment. If it's over 12 calories, then you must wear a full arc flash or beekeeper or Buzz Lightyear type suit, as you can see there. Now, there is a second method for doing that. That's the PPE categories method, or what used to be called the hazard risk categories method. That's still a valid method, but we have typically changed to the newer method for all of our arc flash studies. But if you want to use the older method, you certainly can. These are some arc flash suits, and the highest rating that I know of for an arc flash suit is 100. I'm not saying that there might not be something higher, but that's the highest that I've seen. This is our poster, and we show the three categories, and then down here we have X's on what you need to wear in each of those categories. Undergarments. Now, we talked about this a little bit, but this is very important, and so from this point on, we're kind of through the quick review, and we're going to get into some more interesting things. You are permitted to wear flammable garments, but you are not permitted to wear meltable garments under your PPE. Arc-rated PPE does not guarantee that the materials found in your underwear or clothing will not melt onto your skin during an incident. So the most common clothing that we typically wear as underwear is made of cotton. And of course, that is flammable, but it is not meltable, and that's perfectly fine. But they will say if you have a 12-calorie piece of gear that you're working on and you're wearing garments, if you're wearing PPE that's rated for 12 calories, they will protect you from a second-degree burn unless you are wearing meltable garments under those PPE. And in that case, you could get a third-degree burn, even though it's a 12-calorie piece of equipment and you're wearing 12-calorie PPE, because they will not guarantee you that that underwear couldn't melt. And if it melts, you're pretty much going to get a third-degree burn. All right, 2020 NEC 110.24. Service equipment other than dwelling units shall be legibly marked in the field with the available fault current. So this is a new requirement, and I believe it was new in the 2017 version of NEC, but it hasn't been out for too many years. So the code says that on the service equipment, and only the service equipment, you have to have some kind of a sticker that says what your available fault current is. Well, what we have found lately is that a number of inspectors are saying, that's fine, but we want to know, we want a label on all of the equipment. So that's not a code requirement, but it tends to be required by a number of inspectors. And of course, since we have been required to do this on a number of jobs, we've decided, you know what, it's pretty simple to put that on the arc flash sticker, because when you do an arc flash study, you calculate the available fault current anyway. Why not? Why don't we just put it on the sticker and make it available? So this is our arc flash sticker. I don't have the new one up because we're just changing it right now, but we're going to have another line down here that says available fault current, and we will be putting that available fault current on all of our arc flash stickers. All right, this is the 125 kVA exemption. Now, what does that mean? In the IEEE 1584-2002, it stated, equipment below 240 volts need not be considered unless it involves at least 125 kVA or larger low impedance transformer in its immediate power supply. What does that mean? That was kind of a famous exemption that said if you have mostly a 208 volt transformer and it is smaller than 125 kVA, you don't even need to do an arc flash study. It does not have the ability to give you a second degree burn. And so you could slap a sticker on there that was on anything downstream of that transformer, your panel boards, switchboards, anything downstream, that basically said you were level 0 and that you didn't need to worry about arc flash. Well, in 2018, IEEE came out with a newer version of that standard, and they decided to remove the exemption. And they replaced that with sustainable arcs are possible, but less likely in three-phase systems operating at 240 volts nominal or less with an available short circuit current less than 2,000 amps. Well, what does that mean? Possible, but less likely? Basically, it means that there is no exemption. Doesn't matter. Regardless of what transformer size is there, you have to do the full study. So if you were using that 125 kVA exemption, it's gone. Here's arc rating. Now we talk about arc rating, and really what you're talking about is the arc thermal performance value. So if you have gear, PPE, that's rated for 12 calories, then that means your arc thermal performance value is 12 calories. Here's something I think is fun. ATPV, and we're down at informational note 3, but I think you can see my cursor. ATPV is defined as the incident energy in calories per square centimeter on a material or multi-layer system of material that results in a 50% probability that sufficient heat transfer tested through the tested specimen is predicted to cause the onset of a second degree burn. So I've been telling you all along, if you have 12 calorie gear and you're working on a 12 calorie system, you're not going to get a second degree burn. By the way, I made this in red. It's not in red in the standard, but to me, this is like, what? It doesn't say you will be protected. It says there's a 50% probability you will be protected. Well, that's, what the heck is going on there? Well, it is what it is. But I would say that's the bad news. The good news is this. Number one, it is very seldom that an actual arc flash is going to reach the actual tested value of your gear, your PPE. The second thing that I think is more important is that most of us will wear some type of underwear. So even if you have a pair of shorts and a shirt on underneath that's cotton, that will almost certainly provide 100% protection from second and third degree burns. Now let's make this very clear. Multiple layers operate in arc flash the same way as they operate when you're skiing or in the cold. Multiple layers help fantastically in increasing the arc flash rating. So if you have a shirt that's rated for 2 calories and PPE that's rated for 12, that's probably not going to be 14. It's probably going to be more like 20. And so if you have an underlay of clothing, it adds tremendously to your protection. The caveat there is if you have a shirt that's rated for, let's say, 10, and your PPE is rated for 12, you say, well, I can add those up and now I can work on something that's 12 calories. No, you can't. You cannot work on something that's that many calories unless those two pieces have been tested in combination of one another. So if you have a shirt that's rated 10 and you put coveralls over them that's rated 12, you're still 12. You are whatever the highest of those two pieces of equipment. You can't layer and add the two pieces together under the standard. However, layering does provide a lot of protection. So it's a good thing morally to know that in reality, you are reducing your chance of a burn significantly. So I hope that was clear there. Let's look at leather gloves. Leather gloves are not arc flash rated. And we've talked about arc flash PPE, and what we generally talked about was the balaclava and the harnesses and the face shield and the shirt and the pants and so on. Let's look at some of the other pieces of equipment. Note that heavy-duty leather work gloves or leather protectors worn over rubber gloves are included as arc flash protection. Leather materials, however, are not arc flash rated. However, heavy-duty leather gloves made entirely of leather with a minimum thickness of 0.03 inches that are unlined or lined with non-flammable, non-melting fabrics have been shown to have an arc thermal performance value in excess of 10 calories. So basically, for anything that is within that second group that goes from 1.2 to 12, for the most part, if we have the leather gloves, they're rated 10 calories, and then we have rubber gloves under those leather gloves, we're pretty much going to be good for 12, although this is kind of loose in the standard. Glove classifications are here. It is not required that you put glove classification on your arc flash label, but we do, and most people that I know of that do arc flash studies do, and that shows you your glove classifications. Test intervals. This, of course, is not fun, but gloves should be tested before you use them the first time and every 6 months thereafter. Blankets, 12 months. So you buy a brand new set of gloves, you pull them open. By standard, you can't actually use those gloves until they're tested. And you could take them in and be tested. There are also a lot of people that will drive around and come to facilities and go through and test things for you. Head and face protection. You need to have a face shield with an arc-rated balaclava if you're anything over 1.2. This says down in the red at the bottom, eye protection shall always be worn under the face shields and hoods. Why do you have to wear that? Because the face shield and hood is meant to protect you from burns. It is not meant to protect you from projectiles that could penetrate through that face shield, and therefore you need to wear glasses under that. And of course, that makes it a lot more difficult to work, especially if things start to fog up, but there's the standard. Foot protection is another interesting one. Heavy-duty leather footwear or dielectric footwear provides some arc flash protection to the feet and shall be used in all exposures greater than 4 calories. Footwear with an arc rating is not available. Normally, the employee's feet are less exposed than the hands or head due to the proximity of most tasks. However, employees should not wear footwear made of lightweight materials and so forth. So basically, our standard PPE includes good industrial leather work shoes, but they're not going to have an arc rating. And our experience is that that's okay, that they do tend to protect people, but again, a little bit loosey-goosey in the standards. Outer layers. Do you need to have, if you're going to go up and you're going to wear something like a harness, let's say, does that harness need to be arc flash rated? And the answer is yes, it does. If you have raincoats, if you have harnesses, if you have anything that you wear over your PPE, they need to be arc flash rated, because that arc flash gear is meant to protect you from an arc flash explosion. But if something over you is on fire and literally burning, then none of that arc flash gear is meant to protect you from third-degree burns due to things that you're wearing that are on fire. So anything that you wear over your arc flash gear must be arc flash rated. And those raincoats, harnesses, those types of things, they're readily available in an arc flash rating. Conductive articles, I think this is kind of obvious, but they want to make sure you don't wear conductive articles where that could increase the chance of an arc flash. And normally you're not going to have this kind of stuff, but you know, if you're walking around like this guy with some keys hanging off your belt and your shirt and your pants and everything are arc rated, that's still a violation to have things that are conductive on the outside of your body there. Insulated tools. Insulated tools, a little favorite of mine because I am the proud recipient of a $50,000 fine for not using insulated tools. I've mentioned to you before that I was the director of engineering at Geneva Steel. One day, OSHA came into our plant, and OSHA was in our plant a lot. And they went to one of the electricians and they pulled a wrench out of, or a pair of pliers out of his bag that looked like that. They said, "That's a nice pair of pliers. By the way, do you ever work on energized equipment?" He says, "Are you kidding? Like almost every day." They said, "Thank you." And I got a letter the next day that said, "Greetings from OSHA, you owe us $10,000. Well, you owe us $10,000 for today, but we will fine you another $10,000 tomorrow, another $10,000 the next day, and the next day, and the day after that. And we will continue fining you $10,000 per day until any electrician who works on energized gear has only insulated tools in their bag." So we went down, talked to OSHA, negotiated it, found any place in the nation we could get insulated tools, and ordered insulated tools for all of our electricians, and negotiated a $50,000 fine with OSHA. So it happened to me, it could happen to you. Now, if you have electricians and they don't operate on energized equipment very often, if that guy had pulled out, if the OSHA guy had pulled out this set of pliers and said, "Do you ever work energized?" and the electricians had said, "Yes, we work energized, but not with these tools. Anytime we work energized, we have a special set of insulated tools that we work with," that would have been fine. But it is an OSHA requirement that you use insulated tools. And so, word to the wise, my pocket's $50,000 thinner because of that, and could happen to you. Arc blast, PPE does not have an arc blast rating. So they're saying, yes, we're protecting you from shock, we're protecting you from burns, but we are not going to protect you from falling off a ladder. We're not going to protect you from projectiles that could be injected into you. We're not going to protect you from things that could hit you and so on. So there's no 100% guarantee. And therefore, realize that even if you're all suited up, there still are risks associated from working energized. Now, these are some drives, and I won't talk about this too much, but if you're looking at an arc rating, ask yourself, which drive you would rather have there in the event of an arc flash explosion. Let's take a look now at arc flash mitigation. So we have an arc flash, and let's say that the gear is 30 calories. Well, we don't like 30 calories because none of us likes being in that beekeeper suit. So we look at arc flash mitigation. And in fact, the code now requires arc flash mitigation. I'm not going to discuss this, but these are some theoretical arc flash energy reduction methods that you could use that may work or they may not work. Some of them are pretty good, like using a remote racking device. That's pretty nice. What I'm going to do next is we're going to talk about the code, and we're going to talk about methods that actually do work. Current limiting fuses typically interrupt in less than half a cycle. Low voltage breakers, 1 to 6 cycles. A low voltage insulated case type breaker without an instantaneous element could take up to 30 cycles. Medium voltage breakers could be up to 8 cycles. The old air breakers were 8 cycles. Newer breakers are 3 and 5 cycles. But just kind of an indication of how fast things interrupt. Now, I was an engineer with Westinghouse when they came out with the very first high interrupting circuit breakers. And you know that they have all kinds of ratings on circuit breakers that are 5 kA, 10 kA, 15, 25, whatever. But then the higher interrupting breakers are always 65 and 100. Westinghouse came up with that because if you have a 2500 kVA transformer and a given amount, a reasonable amount of motor contribution, then the fault current from that transformer is going to be 65 kA or less. And that's where the 65 kA breaker came from, to allow engineers to specify 2500 kVA 480 volt transformers. Prior to that time, engineers mostly, and this was in the 80s, Prior to that time, engineers tried to have their largest 480 volt distribution transformers be 1,000 kVA or less, and these days 2,500 kVA is common, and that's because these breakers. Now, a 65 kA breaker will blow up if you put 65 kA through it. A 65 kA breaker cannot interrupt 65 kA. A 65 kA breaker can interrupt a circuit capable of providing 65 kA, but the only way it interrupts is by interrupting very quickly like this. And so pretty much all those 65 kA breakers, unless you get into the really big ones, are current limiting because they can't actually interrupt 65 kA. They just interrupt a 65 kA circuit fast enough that it will never get to 65 kA. So, and fuses, of course, have the same sort of thing. They tend to be current limiting in this manner. Here's NEC 2020, paragraph 240.87, arc energy reduction, where the highest continuous current trip setting for which the actual overcurrent device installed in a circuit breaker is rated or can be adjusted is 1,200 amps or higher. You must have a method of arc energy reduction. So we're talking about circuit breakers, and they're saying if you can adjust that breaker to 1,200 amps or higher, then you must have some form of arc energy reduction. So what if you have a circuit breaker that has an adjustable trip that goes up to 1,200, but you only set it for 900? You are still subject to this interpretation because it could be adjusted to 1,200 amps or higher. What if you have a 1,200 amp frame breaker, but it's got a trip unit, adjustable or not, that does not allow you to set that breaker higher than 1,000 amps? Then you would not be subject to this. So it depends upon the trip device in there. And then it lists the different ways in which you can do arc energy reduction. And notice that number 7 says an approved equivalent means. Now I'm going to talk about these methods of arc energy reduction. I'm not going to read that list. You can scan it by yourself. But we are going to talk about a few things and how the industry is responding to this requirement from the code, and how that may affect your designs. Now, this is an interesting one that a lot of people don't recognize and don't do. NEC 2020 240.87C, performance testing. The arc energy reduction protection system shall be performance tested by primary current injection testing or another method, approved method, when first installed on site. This testing shall be conducted by a qualified person in accordance with the manufacturer's instructions, and you need to have a written method. And at the bottom it says some things cannot be tested. So if you can't test it, so be it. But if you can test it, you're supposed to test it, and it says by primary current injection. So if you have a new switchboard, it arrives on site, it's got a circuit breaker with an arms switch on it, which we'll talk about in a minute. Code says you have to bring somebody in during initiation to do a primary current test on that thing to make sure that it works. NEC 2020 240.67, we have been talking about circuit breakers. What if you have a fuse? Then are there any requirements? Well, it turns out that there are. It says where fuses are rated 1,200 amps or higher are installed, that these things below shall apply. Number 1, you have to have documentation, and it says documentation shall also be provided to demonstrate that the method chosen to reduce clearing time is set to operate at a value below the available arcing current. Whoa, this made things a lot more difficult for design engineers, because they're saying when you select a fuse 1,200 amps or higher, you need to verify that it is going to operate below the arcing current of the system. So, there you go. NEC 2020, this is part B. It says, and again, we're talking about fuses. This was part A. Now we get to part B. A fuse shall have a clearing time of 0.07 seconds or less at the available arcing current. We're not talking about fault current. We're talking about arcing current. How do you know what the arcing current is? Well, you don't unless you do an arc flash study. And so then they have mentioned some other things that you can do with fuses uh, if you don't have that 0.07 seconds. So there are lots of fuse requirements there. Here's some relative costs. Zone selective interlocking tends to be fairly inexpensive. Differential relaying tends to be quite expensive. The energy reducing maintenance switch, which we'll talk about in a minute, fairly inexpensive, and so on and so forth. You can scan through that slide there. Okay, overcurrent protection is a trade-off with coordination. In order to get the best coordination, we generally want to have time delays on the upstream breakers. Whenever you put time delays on the upstream breakers, then you make the circuit more dangerous. And as most people can tell you who have been in arc flash studies for a while, the actual arc flash current tends to be less important than the time it takes to interrupt that current. So this is your short time delay. We use this commonly in engineering. There's your long time delay. You come down here and then you have a short time delay here, which says, I don't want to trip the main breaker to the facility or the main breaker on the switchboard because my swamp cooler shorted. I want to let the breaker closest to the swamp cooler interrupt that. And so what I'll do is just put a little time delay. I'll say 20 cycles of time delay here, and I'm not going to trip for 20 cycles, and that gives the lower breaker time to trip. Unfortunately, anything between this breaker and that lower breaker now has an intentional 20 cycle time delay, and that does wondrously horrible things for your calories. Now, here's time current curve, and this could be, let's say, a fuse. In this area, the fuse is not going to blow. In this area, the fuse is going to blow. And in this area, we don't know. We call this Schrodinger's cat area. Don't have time to really talk about Schrodinger's cat too much, but look it up. Basically, this was a thought experiment back in Einstein's day where Schrodinger put a cat inside a box. Again, it's a thought experiment. He didn't actually do it. And said that depending upon where certain particles were, the cat could be alive or dead. And so it's kind of that same thing here. We don't know whether that breaker is going to trip or whether it's not going to trip. This is the unknown area. And what causes those unknowns? Well, manufacturing variances can cause the unknowns. The temperature at which the breaker or fuse operates, the ambient temperature, could make a difference. The previous loadings on that could make a difference, and so on and so forth. So we don't really know. So how do we look at that area? And generally, when we look at that area from an arc flash point of view, we assume that it is not going to trip because we simply don't know. Now, here is an output from an arc fault study. And you'll notice that it has the bus bolted fault. It has the arcing fault. It has the time delay. And over here, we have the incident energy. And then, of course, there's a number of other things as well. Let's take a look at these top two lines. This is a real job. And we have on this particular circuit, 18,000 amps of fault current. But that is the bolted fault current. If there is an arc, there's an impedance in the arc, and therefore the arcing current is going to be less. The arcing current on that circuit is 6.7. So the arcing current on that circuit is 6,700 amps. It will trip in 0.015 seconds, and our calories is 0.32. So at 0.32, all we need to wear is just shirt and pants that are non-flammable. That's great. Let's take a look at line 2. Line 2, our fault's only 8 calories. So clearly that's less dangerous, right? This is only 8,000, did I say calories? I'm sorry. This is only 8,000 amps, whereas the line above it was 18,000 amps, so clearly a much safer circuit. The arcing fault is only 3,000 amps. That's less than half of what this arcing fault is, so that looks like it's going to be much safer. But let's go over here, and it's got 20 calories. Whoa! Why is that 20 calories? It's not safer. It's much more dangerous. Why? Because it's got a 2-second time delay. Now, why is there a 2-second time delay? We'll read the standard in a moment, but basically they're saying that if the circuit breaker or fuse or what have you trips in less than 2 seconds, we're only going to calculate the incident energy for 2 seconds, because in 2 seconds you can run. And that is literally the truth. We will see the actual statement in a moment. In 2 seconds you can run. So if you'll notice down here, 2 seconds, 2 seconds, 2 seconds, 2 seconds, excuse me. And that means that probably the circuit breaker or switch took longer than 2 seconds, and therefore they only calculated the energy for the first 2 seconds. Here's an example. And again, this is a real example. Here's our, I think this is a circuit breaker. So there's your time delay over current, there's your instantaneous, and here is your arcing fault. You can see that that arcing fault is high enough that the instantaneous trip on the breaker is going to trip. It turns out that that is this first line here. This first line, it's going to trip instantaneously, so our trip delay is 0.015, and we have a very low calories. Now let's look at the second line. Here's the second line. This is in the Schrodinger's cat area. And so is it going to trip or not? I don't know. It looks like it looks like it may trip, but I can't guarantee it's going to trip because it's in that unknown area. And therefore, if this portion of that instantaneous is under the arcing fault, then how long could it trip? Well, let's go right here. We'll go up and over, and that looks to me like 7 or 8 seconds. So in an arc flash, that circuit breaker could take 7 to 8 seconds to trip. Therefore, our program is going to only calculate it for the first 2 seconds, and we're going to get a very high number of calories. So whenever we see this, we want to be careful about, is there any way that we can reduce that instantaneous trip to get it under the arcing fault current? Here's the 2-second rule from NFPA 70E. If the arcing time in equation D4.3 C is longer than 2 seconds, consider how long a person is likely to remain in the location of the arc flash. It is likely that a person exposed to an arc flash will move away quickly if it is physically possible, and 2 seconds is a reasonable maximum time for calculations. So when you're using Easy Power or SKM or any of those, this 2-second rule tends to be the default. If you think there's no way a person could get out of the area in 2 seconds, you can change that, but that tends to be typical for people doing arc flash studies. So here's Schrodinger's cat. He says, "Tell Schrodinger I survived." Some breakers, you can actually turn the instantaneous off. When you do that, you are pretty much going to have a very high calorie level. Now we talk about an arc flash reduction maintenance switch, and I don't have a lot of time to talk about that, but let's take a look at this. I've got a breaker. I want to use a short time delay because I want to maximize my breaker coordination. So I get a breaker with an arc flash reduction maintenance switch. These things are becoming very, very popular these days. And what happens is when I put this in normal mode, then I have my short time delay. When I put it in maintenance mode, it eliminates the short time delay and gives me an instantaneous trip. Therefore, I'm going to put it in normal mode when I'm not working on equipment. When I work on the equipment hot, I'm going to put it in maintenance mode. It eliminates the short time delay, and my calories may come down from 30 to 1 or what have you. Now here's my concerns, and I struggle with this a lot. Where is that arm switch located? Well, typically the arm switch is going to be located in another piece of equipment. So if you're working on a motor control center, the arc flash rating on that motor control center is going to be the arc flash coming into the motor control center, because at least in the main breaker section. In the main breaker section, if you have an arc flash, it could cause an arc on the primary terminals of that main breaker, and therefore the thing that's going to interrupt that is going to be the piece of equipment that feeds that motor control center. So where is that? Typically in another location, in another piece of equipment. How does the worker know he needs to turn that switch to maintenance mode? And what calorie do you print on the label of the motor control center? Do you print there the calorie in maintenance mode, or do you print there the calories in normal mode? And we tend to say that we want to print the calories in maintenance mode because you shouldn't be working on it if it isn't in maintenance mode. But then we put a big warning right on the arc flash sticker that said you must turn the arm switch to the maintenance mode, and here's where that breaker is. So some concerns, and that shows what happens when you go off and on. Here's zone selective interlocking. That certainly is a way of having your cake and eating it too, as they say. So you can have your short time delay, but in these zones, if you have zone selective interlocking, it can trip instantaneously. Differential relays, the same thing. These tend to be expensive, but they can provide quick trips. This is, let me put it here, this is a shorting bar. Whenever you have a high current, this thing actually shorts on the primary of the breaker and causes a very high current to flow, in addition to extinguishing the arc fault because you've just shorted this current here. Never seen one of these in practice, but they do exist. This is fairly common. This is another method that you can use, and that is an arc flash relay. Instead of looking at the current, you can look at light. And so you can look at light and you can have a time delay, but have an instantaneous trip in case there is an arc flash by using the fiber optics in there to sense the actual appearance of light. Now remember that that's going to sense the appearance of light here, and it may help you in these points that are fed by the main breaker. It may not help you on the primary of the main breaker. Can you use an arc flash relay to lower PPE levels? Yes, this is very well established, and there is a little fuse document to indicate that these are very well established, that you can lower your PPE levels using some of these other methods. And can you use popular engineering software packages to model an arc flash relay? The answer is yes. And this again is an explanation of that I'm not going to read because I want to get into just a couple more things before we stop, and we've only got a couple more minutes. Once an instantaneous override that says no matter where you set the instantaneous, some breakers will go ahead and trip instantaneously at a certain level, and so that can be used for arc flash mitigation. Let's go here. If you have a panel like this and you have an arc flash, and this, let's pretend this is your main breaker. It may or may not be on this panel, but what is your arc flash? It'll be the arc flash coming in to that panel. It will not be the arc flash on the secondary side of that main breaker. And since there are no metallic barriers in here, then the whole switchboard has to be rated for that number of calories. On the other hand, if you have a situation like this in which you have multiple vertical sections and they are isolated by a metallic barrier between them, then this section can have a calorie rating based on the calories coming into the gear. The rest of your gear can have calorie rating based upon the secondary side of that main breaker. How do we know that that's possible? Because it's right here in 1584, and I'm not going to read that all, but 1584 says that basically what I explained to you is very much kosher, and we can do that. So if you have a situation like this, you can have two labels, one for this incoming gear and then one for the other sections. Or if you want, you could just take the higher calorie level on the incoming gear and label your whole panel that. There is nothing to prevent you from doing that if you would like to do it. High resistance grounding does not help you reduce your PPE levels, but it does provide a greater amount of safety because it limits your phase to ground current, and it makes it much safer for those who are using high resistance grounding. And finally, we get into our arc flash risk assessment. We do the arc flash study, then the equipment labeling and modification, provide appropriate PPE and tools, implement a training program, document, and then you have to review your arc flash every 5 years. That review simply amounts to, has anything changed? And if it has, then you need to update in order to add those changes. If nothing has changed, you're done. You've already done your evaluation. So we are out of time, and thank you for being with us today. I hope there will be something in that presentation that will be of interest to you. And at this point, we're happy to take the presentation is over. We'll be happy to answer some questions, and I see that we have a few.
Great, I will help fill those for you. Our first question that came in from David. Is there a minimum arc flash rating in which you don't have to label?
Say that again, in which you don't have to what?
In which you don't have to label.
Oh, yeah, the answer is no. It used to be that 125 kVA exemption would allow you to put on generic labels, but that's gone now. So basically, you have a switchboard, a panel board, what have you. It doesn't matter what the calories are. You must have a label.
Great. The next one is asking if we utilize SKM or Easy Power to perform the analysis.
Yeah, that's a good question. My company uses SKM, and we use SKM primarily because we saw a lot of specifications for arc flash requiring that you use SKM, and a lot of the engineering companies will use SKM. But I am not here to say SKM is the best. I have talked to a lot of people who use Easy Power, and I think that's a very fine program. So we use SKM. Some engineers actually have both. A lot of government uses Easy Power, and there's also another program that all of a sudden escapes my brain. But Easy Power is a great program. We have no problem with it.
Great. Next is, can you give me your opinion on what the term work means in regard to when you suit up in the proper gear?
To the work, right?
Yeah, what does work mean in regards to when you suit up in the proper gear?
Yeah, so in general, when you're talking about working, you're talking about that likelihood of occurrence. So let's say that you are doing an arc flash study. So you have somebody suit up, they open the door so you can take a picture of the breaker and the cables coming into the breaker, and then they step away from that area. Now, a person taking a picture of that can walk within 1 foot because of the likelihood of occurrence and take a picture. But they can only take a picture if nobody is actually doing anything. If they've stepped away from the gear and they're not actually doing anything on the gear. Now, if there is somebody in there, they're taking voltage measurements, they're putting CTs around to measure current, they're moving a wire so that they can read that, all of that would be considered work. And if there's any kind of work that's going on, then you cannot be within the arc flash boundary without your burn gear on it. And so I would generally say, for the most part, the definition of work means that somebody is in the restricted space. And if there's somebody in that restricted space that is within 1 foot of the gear, then I say no matter what's happening, work is going on. So if somebody's in the restricted space, I would say work is happening. And in that case, you are going to have to act appropriately. And you're going to have your arc flash gear. And you can't come in there and do infrared or arc flash because there is work going on. I hope that answered that question.
Great. The next question is, if you have a breaker that is underrated for short circuit current, do you place a blast hazard label on the panel, and means to disconnect will have to be done upstream?
No. If you have, now, I kind of like the idea. I mean, if you put a label there that says, hey, there's something dangerous here, and you disconnect upstream, that's a good idea. But when you disconnect, typically there's not going to be a fault occurring. The problem is if there's a fault occurring at any time, that breaker could blow up and create a hazard. So if you have a breaker that's underrated, you have to change it. That's all there is to it. And I know that's a pain in the butt because breakers many times are not easy to change, especially if they're an older breaker. And sometimes you have an older facility, you don't have a lot of money. It's very difficult, but if it's underrated, you have to replace that with a breaker or fuse that is properly rated, or you have to have a breaker or fuse above that that is series rated with that breaker at the appropriate interrupting rating. So if you have a series rating, and that's in the yellow book there, the UL yellow book, and you can say, okay, my breaker may be only rated 25 kA and the fault's 35 kA, but the fuse above it is series rated so that the combination is rated at 60 kA, then you're perfectly fine. You don't have to have any labels at all. But the arc blast rating doesn't make this thing legal, or the blast message does not make it legal.
Great. Next question. Does molded case breaker have to be injected tested, or does the exercise yearly count as still suitable?
According to that paragraph I showed you in the code, it needs to be injection tested, but remember that we're only talking about injection testing for breakers that have arc flash mitigation on them. So there isn't a requirement during the startup that you test all your breakers. You only have to have to test the ones that have arc flash mitigation on them, such as an arm switch. With other breakers, there isn't that requirement for injection testing.
Okay. This next question, I believe, was submitted in two parts. If it doesn't make sense when I combine them, let me know. Is arcing fault typically 1/3 of the bolted fault in reference to ground?
Okay, arcing fault, I usually say is like somewhere between 30 and 85% of the bolted fault. You cannot, but here's the thing. There have been all kinds of tests done to determine what arcing fault is. This isn't, if you look at bolted fault, that's a pretty simple calculation that we all learn in engineering school, and it's very straightforward. Arcing fault is not that straightforward, and recently IEEE came out with a new standard of IEEE 1584 in 2018, in which a lot of the calculations for determining the arcing fault changed, and they changed because of testing that had been done. So there simply is no way to look at the bolted fault, multiply it by some number, and know what the arcing fault is. It is way, way, way more complicated than that.
All right. The next question we have is, our facility has the arc flash labels from 2014. Do we need to reassess the labels?
Yeah, and the answer is no, you were good. But here's what I would do is walk into your facility, ask yourself, has anything changed? And if you added a panel board over someplace, well, all you need to do is add an arc flash sticker to that panel board. But if you came in and you put in a new transformer, let's say the utility put in a new transformer that's much bigger or even smaller, or you change the whole distribution system, yeah, then you are going to want to go ahead and reevaluate that. But for the most part, you don't. And arc flash stickers are grandfathered. So it doesn't matter when they were put on, as long as they were legal and accurate at the time that they were installed, you'd never have to change them. Now, I'm saying that in 2021, they could come out and say, okay, now we're not going to let you grandfather anymore or something, but I don't think they're going to do that. I really think that this is going to be the case. They've pretty much made a precedent of that. Arc flash stickers never expire, and the only reason you need to replace them or reevaluate them is if you made a significant change to your power distribution system.
All right. The next question is that someone noticed some pictures with balloons or rectangles over vent holes and cooling equipment in the panel enclosures. How big can the holes be in an enclosure or made by some maintenance crew? Normally temperature management, but also for custom enclosures.
Yeah, this is interesting. So you're saying if you got some little holes in the box, does that affect your calories or your arc flash rating or when you need to wear arc flash gear? And the answer is there may be something out there, but I am not aware of it. If I've spent quite a bit of time in NFPA 70E, and I have never seen anything like that in the standard. And I've never seen anything like that in NFPA 70E. So I remain open to being wrong about that. There may be a standard out there that does specify that, but if there is, I am not aware of it. So my advice would be basically make a subjective judgment call. If it looks dangerous, it probably is dangerous.
Next is how do you compare SKM and ETAP?
Yeah, ETAP, thank you. That's the one I forgot. So there is ETAP, there is Easy Power, and there's SKM. Those are the three that are in common usage. And it seems like utilities and a lot of government people are required to use ETAP. It was basically developed for utilities. Easy Power and SKM are both more private. SKM came out first, and so they kind of had a jump on the market. But here's the thing. I personally haven't used all those three enough to make a fair evaluation. What I have done is everywhere I go, if somebody says, oh, I use ETAP or I use Easy Power, then I ask them, what's your opinion of that? And many engineers have, they may have all three, or they may have ETAP and SKM, or Easy Power and SKM. And some engineers actually are pretty fluent with both. And so I'm always interested in what they have to say. And the results of my asking engineers about this are that the best program is the one that you're most familiar with. Each of them does a very good job. Each of them uses the formulas from IEEE 1584. So in terms of calculations, they're all identical. And I would say it doesn't really matter. I think they all do a very good job. And I don't think any one of them really has a big advantage on the others in terms of doing an arc flash study. I think it just depends on what you're most familiar with.
All right. Thank you, everyone. It looks like that's all the questions we had. So we want to thank you again for joining and invite you to be with us next time.